In fact, at this very moment, you are a passenger on a vessel called the Milky Way, hurtling through the cosmos at over 2 million kilometers per hour. We aren't just drifting, we are falling. For billions of years, every civilization that ever graced this planet has shared a single destiny, being dragged toward a mysterious entity hidden behind the dust-choked wall of our own galaxy. A place astronomers call the Great Attractor. Yet, there is a truth even stranger than that colossal pull. Despite falling faster than anything humanity has ever built, we will never arrive. Tonight, join me as we seek an answer to a haunting question. Where is home? When everything is falling forever. For most of human history, the sky appeared fixed and serene. A backdrop rather than a participant. Something to be observed and catalogued rather than something actively happening to us. Even after Edwin Hubble established in the 1920s that galaxies were real objects outside our own, scattered across distances that reduced the Milky Way to a single grain of sand on an infinite beach, the dominant picture of the universe remained essentially calm. Yes, the universe was expanding. Space itself was stretching outward in every direction, carrying galaxies apart the way dots on the surface of an inflating balloon drift away from one another. Yes, galaxies were receding from us at speeds proportional to their distance, but this recession was universal, uniform, symmetric, the same in every direction. A tide that lifted all ships equally. Nobody was going anywhere special. Everything was just spreading out. The first crack in that picture appeared in 1973, when astronomers noticed a subtle asymmetry in the temperature of the cosmic microwave background, the faint thermal radiation left over from the Big Bang that permeates the entire universe like permanent background static. One side of the sky read fractionally warmer than the other. The difference was less than 1/100th of a degree Fahrenheit, a gap so minute that any thermometer designed for human use would register it as 0. But in a universe that was supposed to expand identically in every direction, any asymmetry at all was a contradiction. And physicists do not ignore contradictions. A warmer side meant the Milky Way was physically moving toward it, compressing the wavelengths of incoming radiation slightly the way the pitch of a passing ambulance rises as it approaches. Strip away the expansion of space. Subtract what the universe was supposed to be doing anyway. And what remained was a raw, unexplained velocity of approximately 600 kilometers per second, aimed at a specific point in the southern sky. 600 kilometers per second, the fastest object humanity has ever launched into space travels at roughly 700 kilometers per hour at orbital altitudes, which means the unexplained motion of the Milky Way is about 3,000 times faster than the International Space Station moving overhead. It is fast enough that, sustained over 50 million years, a blink in cosmic time, roughly the duration since large mammals first appeared on Earth, the Milky Way would cover a distance equal to its own full diameter. This was the peculiar velocity, the motion of our galaxy that had nothing to do with expansion, that pointed at a specific direction in space, that had no identified cause, and that would dominate the field of observational cosmology for the next 4 decades. What made the peculiar velocity deeply unsettling was the company it kept. The Milky Way was not the only galaxy moving this way. The Andromeda Galaxy, our nearest large neighbor, sitting 2.5 million light-years away, roughly 25 times the diameter of the Milky Way itself, was carrying the same drift in the same direction. The local group, the collection of roughly 50 galaxies that constitute our immediate gravitational neighborhood, was moving as one. Beyond the local group, the same signal appeared in galaxy after galaxy across a volume of space spanning hundreds of millions of light-years. Everything was tilting toward the same invisible point, flowing toward it at speeds that varied depending on distance and angle, but all pointed to a shared source of gravitational attraction somewhere ahead. Whatever was pulling on us was not targeting us specifically. It was exerting its influence across a region of space so large that entire galaxy clusters, structures containing thousands of individual galaxies each, were being swept along in the same direction, like leaves caught in a current that originated somewhere upstream and out of sight. The size of the pull implied an extraordinary concentration of mass at the source. Working backward from the observed velocities, astronomers calculated that the attractor, whatever it was, would need to carry a gravitational influence equivalent to roughly 10,000 trillion times the mass of the Sun. That number requires some unpacking. Our entire Milky Way, with its hundreds of billions of stars and its vast clouds of gas and dust and dark matter, accounts for approximately 1 trillion solar masses. The thing pulling us was exerting the gravitational force of 10,000 Milky Ways, and nobody could find it, because the direction it occupied in the sky happened to coincide precisely with the most impenetrable region of the observable universe. The dense, dust-choked plane of the galaxy we were already living inside. This is where the story gets genuinely strange. The object or region responsible for dragging us across the cosmos at 2 million kilometers an hour was hiding in plain sight. Or more accurately, hiding behind plain sight, concealed not by distance or darkness, but by the luminous body of our own home galaxy, which was generating so much dust and gas and stellar light in that direction that optical telescopes simply could not see through it. The attractor was not in some remote corner of the observable universe. It was relatively close. By cosmic standards, it was just permanently behind a curtain that the Milky Way itself had drawn across that section of sky. Astronomers began calling that curtain the zone of avoidance, a strip of sky running along the plane of the galactic disk where optical observations were effectively impossible, where roughly 20% of the extragalactic sky was hidden behind layers of interstellar dust dense enough to block visible light completely. It was named, with characteristic astronomical bluntness, by Edwin Hubble himself, who noticed that his early catalogues of galaxies showed a conspicuous absence along the galactic plane and concluded, correctly, that dust extinction was erasing whatever lay beyond. For decades, the zone of avoidance was simply accepted as a limitation, a blind spot in humanity's cosmic map that we would have to work around. And for a long time, the Great Attractor, the name that had not yet been coined, sat invisibly inside it, pulling on us with 10,000 galaxy masses of gravitational force while we stared at the sky and wondered what we were missing. The answer came in 1987, from 7 astronomers working simultaneously across multiple institutions, a collaboration that would acquire a nickname partly for its dramatic results and partly because their work really did carry something of the quality of a samurai expedition into dangerous terrain. Alan Dressler, Sandra Faber, Donald Lyndon Bell, Roberto Terlevish, Roger Davies, Gary Wegner, and David Burstein spent years measuring the peculiar velocities of hundreds of elliptical galaxies scattered across the sky. Using the relationship between a galaxy's luminosity and the speed at which its stars orbit to derive independent distance, estimates that could be compared against the redshift predictions of the Hubble flow, the technique was painstaking, requiring careful calibration and statistical rigor, and the results, when they finally came together, were, by the standards of a field accustomed to incremental progress, astonishing. The universe was not homogeneous. The peculiar velocities were not random. Hundreds of galaxies across an enormous volume of space were moving in coordinated fashion toward a shared gravitational focal point, streaming like water, finding the lowest point in a landscape. And the focal point lay at a distance of approximately 150 to 250 million light-years in the direction of the constellations Norma and Triangulum Australe, almost perfectly aligned with the zone of avoidance. The Seven Samurai, as they came to be known, named their discovery the Great Attractor, a gravitational anomaly of unprecedented scale that was simultaneously the most powerful nearby structure astronomers had ever identified, and the least observed, hidden behind the one thing they could not look through. The name was not an overstatement. It was a region of space exerting gravitational dominance over a volume containing millions of galaxies, pulling on structures separated by hundreds of millions of light-years, influencing the motion of more matter than most cosmological models had predicted could ever be concentrated in a single region at this stage of the universe's evolution. And it was sitting invisibly in the sky, the most important nearby feature of the cosmic landscape, unobserved and unnamed for decades, while it quietly shaped the trajectory of everything in our corner of the universe. What lay inside it, what specific structure or accumulation of mass was generating this extraordinary pull, would take another decade to even partially answer. And the answer, when it came, would force a complete rethinking of what kind of structure the universe was capable of producing at the largest scales. The Seven Samurai's paper, published in the Astrophysical Journal in March of 1988, covered 214 elliptical galaxies across roughly two-thirds of the sky, accessible from their observatories, and derived peculiar velocities that, when mapped together, showed a coherent streaming motion with a bulk velocity amplitude of approximately 600 kilometers per second, directed toward a point in the zone of avoidance. The statistical significance of the result was strong enough to rule out random variation as an explanation. The coordinated motion was real, but the reaction from the broader astronomical community was cautious, and in some quarters, openly skeptical. The implied mass concentration was so large, so far beyond what any previous survey had suggested should be present in our local universe, that many astronomers suspected a systematic error in the distance measurements, a bias in the galaxy sample, or some other methodological artifact that would dissolve under independent scrutiny. Subsequent surveys over the following decade, using different galaxy samples and independent measurement techniques, confirmed the basic finding with sufficient consistency that the skepticism gradually gave way, not to certainty, but to the recognition that the Seven Samurai had detected something real, something that the existing maps of the universe had missed, and something that would not be fully understood until the maps were substantially improved. Before the identity of the Great Attractor could be established, astronomers had to find a way through the wall, to look past the one thing that had been blocking their view and confront what had been hiding there all along. Every map of the universe ever drawn by human hands contains a hole. It runs along the equator of our galaxy like a scar, a strip of sky roughly 20 degrees wide on either side of the galactic plane, where the density of interstellar dust and gas is so extreme that optical light from extragalactic sources is absorbed entirely before it can reach a telescope on Earth. Stars in the foreground blaze through in their billions, bright and detailed and countable, but the galaxies behind them are simply gone, erased by the cumulative opacity of thousands of light-years of material between us and them. The zone of avoidance does not look dark. It looks full of Milky Way, full of our own galaxy's interior. And that fullness is exactly what makes it impenetrable to visible light observation. The consequence for cosmology was straightforward and uncomfortable. Roughly 20% of the extragalactic sky was simply unmapped. Any attempt to understand the large-scale distribution of matter in the universe was working from an incomplete dataset, with a systematic blind spot precisely in the region that turned out to matter most, because the Great Attractor, the gravitational center toward which our entire neighborhood was streaming, lay almost exactly in the densest part of the zone of avoidance. The most important nearby structure in the observable universe was also the least observed. Astronomers could infer its existence from the motion of galaxies they could see. They could calculate its approximate mass and position from the peculiar velocity field it generated. But looking at it directly, studying its constituent galaxies and clusters, mapping its internal structure, all of that required getting past a wall of material that absorbed visible light as completely as if it were not there. The solution was to stop using visible light, infrared radiation, longer in wavelength than the red end of the visible spectrum, penetrates dust much more effectively than optical light. And by the 1990s, infrared surveys were beginning to reveal individual galaxies shining through the galactic plane like embers visible through smoke. The 2-micron all-sky survey catalogued hundreds of thousands of sources in the zone of avoidance, and among them were galaxies, real extragalactic objects that had been invisible to every optical telescope ever pointed at that region of sky. More powerful still was X-ray astronomy, which could detect the extremely hot gas that fills the space between galaxies in massive clusters. The clusters in the Zone of Avoidance project, using NASA's Einstein Observatory and later X-ray satellites, began mapping the distribution of galaxy clusters in the hidden region. And what it found confirmed something important. There was indeed a massive concentration of galaxies in the direction of the Great Attractor, centered on the Norma cluster, a dense accumulation of large, old galaxies at a distance of approximately 220 million light-years, many of them actively colliding and radiating powerful radio emissions as they merged. The Norma cluster was real, massive, and gravitationally dominant over its immediate surroundings. Its identification placed a concrete object inside the previously abstract concept of the Great Attractor, giving the gravitational anomaly a physical address and a visible face. But the X-ray surveys also revealed something that complicated the picture considerably. The Norma cluster, large as it was, accounted for only a fraction of the gravitational influence that the peculiar velocity field implied should be there. The original mass estimates for the Great Attractor had placed it at something like 10,000 trillion solar masses. The Norma cluster and its surrounding structure, even accounting for the dark matter that was presumably distributed throughout the region, came in at roughly 10% of that figure. The motion of the Milky Way and its neighbors was being generated by something considerably more powerful than what the Zone of Avoidance was concealing. This revision forced a broader view. If the Great Attractor was only contributing 44% of the Milky Way's peculiar velocity, a figure derived from a comprehensive survey that finally mapped the cluster distribution across the entire sky, then the remaining 56% had to be coming from somewhere else, somewhere farther away, larger, and even less explored. And the data pointed in a clear direction behind the Great Attractor. At roughly 4 times the distance, lay a structure that had been noted in galaxy catalogs since the 1930s, but whose full gravitational influence on the local universe had been consistently underestimated: the Shapley Concentration, named for the astronomer Harlow Shapley, who first identified it as an unusual density of galaxies in the constellation Centaurus, was the largest concentration of matter in the nearby universe, a structure containing thousands of galaxies in a region spanning approximately 260 megaparsecs, with a high-density core of 11 interacting clusters at its heart, whose combined mass approached 13,000 trillion solar masses. The Shapley concentration was pulling on the Great Attractor the way the Great Attractor pulled on us, drawing the entire regional flow of galaxies toward itself at a scale that dwarfed anything previously identified in our cosmic neighborhood, and it sat 650 million light-years away, far enough that its influence arrived, diluted, and distributed. A slow gravitational tide, rather than the sharper local pull of the Norma cluster, but persistent enough and massive enough to account for a significant fraction of everything that was moving in our vicinity. The zone of avoidance continued to yield surprises as observational techniques improved. In November of 2024, a team using the Meerkat radio telescope array in South Africa published a blind survey of the Vela region of the zone of avoidance, detecting hundreds of previously unknown galaxies and finding evidence for an entire supercluster, the Vela supercluster, that had been invisible to optical surveys and was estimated to contribute at least 50 kilometers per second to the motion of the local group, a contribution that had simply been missing from every velocity model that predated radio surveys of the region. The wall was not impenetrable, it was just very, very deep, and every new instrument that could see through it in a different wavelength revealed another layer of structure that had been influencing our motion without our knowledge. The Great Attractor, in other words, was not a single object. It was a region of space defined by its gravitational effects, a complex, layered accumulation of clusters and superclusters and dark matter concentrations, some of them visible in X-ray and infrared, some of them still hidden in the most opaque regions of the zone, all of them contributing to a gravitational pull that had been operating on us since long before there was a humanity to notice it. Understanding what it was required not just better telescopes, but a fundamentally different way of thinking about what kind of structures the universe could produce. And in 2014, that new way of thinking arrived in the form of a single paper published on the cover of Nature magazine, which redrew the boundaries of our cosmic home in a way that nobody had anticipated. The discovery that followed did not just identify the source of the pull, it gave us an address, and in doing so, forced an entirely new understanding of what home could mean on a cosmic scale. Before September of 2014, the standard answer to the question of which supercluster the Milky Way belonged to was the Virgo supercluster, a loose aggregation of galaxy groups and clusters centered on the Virgo cluster, spanning approximately 100 million light-years and containing something on the order of 1,000 large galaxies, along with their smaller satellite systems. The Virgo supercluster was our cosmic region, our local chapter of the universe's larger organization, the structure above the local group in the hierarchy that ran from planet to solar system to galaxy group to galaxy cluster to supercluster. It was a reasonable answer, established by decades of observations, and it was wrong. Or rather, it was incomplete in the way that every previous answer to the question had been incomplete, seeing only the room and missing the building. The team that corrected it was led by R. Brent Tully of the University of Hawaii, working with Helene Courtois, Yehuda Hoffman, and Daniel Pomered. What they did differently was deceptively simple. Instead of mapping where galaxies were located, they mapped how galaxies were moving, peculiar velocities. Those deviations from simple Hubble expansion that had caused so much confusion since the 1970s turned out to contain encoded information about the gravitational landscape of the universe, in the same way that the direction of water flow encodes information about the topography of a watershed. Water does not flow randomly. It follows the gravitational gradient of the terrain, finding the lowest point in its basin and converging there. Galaxies, subjected to the gravitational landscape shaped by the distribution of all the matter around them, do the same thing. Map the direction and speed of enough galaxy motions, and the shape of the underlying gravitational structure emerges like a topographic map drawn from flow patterns rather than elevation measurements. Using a catalogue of peculiar velocities for galaxies across an enormous volume of space, gathered over decades from telescopes around the world and processed through sophisticated reconstruction algorithms, Tully's team found the boundaries of the basin of attraction containing the Milky Way. These boundaries were defined by the lines along which galaxy motions diverged, the cosmic equivalent of a continental divide, where water on one side of the ridge flows to one ocean and water on the other side flows to another. Within the basin, All galaxy motions converged inward, toward a shared gravitational focal point. The basin defined by these flows turned out to be 500 million light-years in diameter and to contain approximately 100,000 large galaxies. With a total mass of roughly 100 million billion solar masses, a number that requires a moment to absorb, since it represents the combined gravitational mass of 100,000 structures, each comparable to the Milky Way, distributed across a volume of space in which the Milky Way itself was a single, small point near the outer edge. Tully's team named it Laniakea, from the Hawaiian words Lani and Akea, immense heaven. The name was chosen to honor the Polynesian navigating tradition, whose practitioners had used the stars to navigate the Pacific Ocean across distances that, at human scales, were as forbidding and featureless as intergalactic space, crossing thousands of kilometers of open water by reading subtle patterns in stars, waves, and winds with a precision that European navigators with compasses and charts could not initially match. The name carried an additional resonance. The Milky Way sat at the outermost margin of Laniakea, near what Tully himself described as the equivalent of a continental divide. At the boundary between our basin and the neighboring Perseus-Pisces supercluster, we were not at the center of home. We were at the edge of it. One small galaxy perched at the rim of a watershed that extended 500 million light-years inward toward a gravitational heart. We had been moving toward all along. That gravitational heart was the Great Attractor. The Laniakea discovery did not diminish the Great Attractor. It recontextualized it. The anomalous pull that had puzzled astronomers since the 1970s. The invisible mass concentration that the Seven Samurai had detected through the motion of hundreds of galaxies and given a name that suggested something exotic and singular. It turned out to be simply the center of a structure we were already inside. The Great Attractor was not an outside force acting on us. It was our gravitational home base. The bottom of the bowl in which the Milky Way had been sitting for billions of years. The focal point of a supercluster so large that even after decades of study, we had not recognized we were part of it. The mystery of what was pulling us resolved, at least partially, into the more ordinary but no less remarkable fact that we were, as Tully put it, discovering for the first time that our hometown was part of a much larger country than we had ever suspected. The Virgo supercluster, which had previously served as our cosmic home, did not disappear in this revised picture. It became a neighborhood within Laniakea, one sub-region of the larger structure, the part of the basin closest to our local group rather than the whole basin itself. The hierarchy had simply extended outward one more level. The way each generation of cartographers discovered that the territory they had been calling the world was actually a peninsula of something larger, and the motion of the Milky Way toward the Great Attractor was revealed as a natural consequence of living inside a basin with a gravitational center. We were not being pulled by an external force so much as we were flowing, slowly and persistently, toward the lowest point of the landscape we inhabited. What the Laniakea discovery also clarified was the scale of coordinated motion in the universe. Within the volume of the supercluster, the motions of galaxies were not random. They were organized, structured, convergent. Every galaxy in Laniakea was moving, to varying degrees, influenced by local gravitational perturbations, toward the same central region, the same Great Attractor, like all the rivers in a continent's drainage basin moving toward the sea. The gravitational landscape of 100,000 galaxies distributed across 500 million light-years was coherent enough, consistent enough, stable enough over billions of years to produce measurable flows that Tully's team could detect and map with a catalogue of peculiar velocities. This was large-scale structure behaving as a unified gravitational system at scales that previous generations of astronomers had assumed were too large for such coherence to be possible. And yet the story did not stop there, because at the same time that Laniakea was clarifying our position within one layer of cosmic structure, the data was already hinting at another layer beyond it. Something larger, farther, and in many ways even more surprising, whose gravitational influence on the local universe had been accumulating in the background of every peculiar velocity measurement ever made. The map of Laniakea was the most detailed picture of our cosmic home that science had ever produced. But even as it was being drawn, the same team was detecting currents flowing beyond its edges. And following those currents led to a discovery that made Laniakea itself look like a sub-district. Harlow Shapley first noticed it in 1930, scanning photographic plates of the southern sky from the Bruce telescope at Bloemfontein, South Africa, as part of a systematic survey of galaxy distributions. In the constellation Centaurus, there was a concentration, a region where galaxies appeared in unusual density, packed more tightly together than surrounding areas, forming what Shapley described as a striking cloud of remarkable linear dimension and numerous population. He measured its distance at roughly 230 megaparsecs, placing it at what was then the outer boundary of the known extragalactic universe, and moved on. The concentration was catalogued, given a designation, and largely overlooked for the next half-century, during which the field of observational cosmology developed tools sophisticated enough to eventually take it seriously. By the time the clusters in the zone of avoidance surveys were mapping the Great Attractor in the early 2000s, Shapley had acquired a more complete identity. Spectroscopic surveys had confirmed it as the largest mass concentration in the nearby universe, a structure spanning approximately 260 megaparsecs, with a high-density core containing 11 interacting galaxy clusters, including 2 major merging systems whose X-ray emissions indicated cluster collisions of extraordinary energy. Its total mass was estimated at 13,000 trillion solar masses, a figure that placed it in a category well beyond anything in the Laniakea region. The Great Attractor, at its revised mass estimate, contained roughly 10% of that. The Shapley concentration was pulling on the Great Attractor the way a mountain pulls on a hill. The same kind of force, operating on the same kind of structure, but at a scale that made the local anomaly look modest by comparison. The critical measurement came from a comprehensive X-ray survey that finally mapped the full cluster distribution within 800 million light-years of the Milky Way, the first survey to account for galaxy clusters in every direction, including through the zone of avoidance. When the gravitational contributions of every identified cluster were calculated and summed, the Norma cluster and the Great Attractor region accounted for approximately 44% of the Milky Way's peculiar velocity. The remaining 56% was attributable to the large-scale flow toward the Shapley concentration, a flow that was not specific to us but encompassed the entire Laniakea region, drawing the supercluster as a whole, all 100,000 galaxies, all the mass of 100 million billion solar masses, in the direction of a structure 4 times farther away and considerably more massive than the local attractor we had been studying for decades. What this meant, in practical terms, was that the Great Attractor was itself being pulled. The gravitational center of Laniakea, the focal point of our entire home supercluster, was moving toward Shapley the way our galaxy was moving toward it, as part of a hierarchy of gravitational flows that cascaded upward from the smallest scale to scales that pushed against the limits of what current surveys could map. The Milky Way flowed toward the Great Attractor as part of Laniakea's internal dynamics. Laniakea flowed toward Shapley as part of a still larger current, and in 2024, a new paper published in Nature Astronomy, a collaboration led by Tully's group at the University of Hawaii, alongside researchers from the Leibniz Institute for Astrophysics in Potsdam and the University of Paris-Saclay, used a catalogue of 56,000 galaxies and a new technique for mapping basins of attraction to suggest something that made Laniakea itself appear to be a substructure within a vastly larger framework. The findings were expressed in probabilistic terms because the data were at the edge of what current surveys could resolve a 60% probability that the Milky Way, along with the entire Laniakea supercluster, actually resided within a gravitational basin centered on the Shapley Concentration, a basin potentially 10 times larger in volume than Laniakea, encompassing a region of space so enormous that existing redshift surveys might not extend far enough to map its full extent. If confirmed, this would mean that the sequence of discoveries that began with the first detection of our peculiar velocity in the 1970s had followed a pattern of nested revelations. The Milky Way belonged to the local group, which flowed toward the Virgo supercluster, which turned out to be a subregion of Laniakea, which might itself be a sub-basin within a structure anchored by Shapley. And Shapley might in turn be embedded in something still larger that current instruments could not yet see. Each answer produced a new question whose scale was 10 times larger than the previous one. Co-author Ehsan Korkchi of the University of Hawaii summarized the situation with a sentence that captured both the achievement and the limitation simultaneously. Our cosmic surveys may not yet be large enough to map the full extent of these immense basins. He said, "We are still gazing through giant eyes. But even these eyes may not be big enough to capture the full picture of our universe." The humility in that statement is worth sitting with. The most powerful telescopes in human history, surveying the velocities of 56,000 galaxies distributed across billions of light years, may be detecting the local features of a structure whose far edge lies beyond what we can currently observe. The map of home keeps expanding, and every expansion reveals that what we thought was the whole was only a room. There is a question that has been building since the very first measurement. Since the moment those early surveys detected the first asymmetry in the sky and calculated that the Milky Way was moving towards something at 2 million kilometers per hour, the question is not just what is pulling us, but what happens when we get there. And the answer involves a force that makes the Great Attractor seem, in relative terms, almost gentle. The pull is real, the motion is real, at 600 kilometers per second, directed toward the gravitational center of a structure containing 100,000 galaxies and 100 million billion solar masses. The Milky Way is genuinely, measurably, persistently moving toward the Great Attractor, and has been doing so for as long as the supercluster has existed, which is most of the history of the universe. This is not ambiguous. It is one of the most precisely measured large-scale motions in observational astronomy, confirmed by multiple independent methods using different instruments, different techniques, and different datasets, all converging on the same velocity, the same direction, the same destination. The Milky Way will never get there. This is not a statement about timescales, the way it would be if someone said that the nearest star is so far away that any journey to it would take longer than human civilization has existed. It is a statement about physics. The peculiar velocity carrying us toward the Great Attractor represents approximately 20% of the velocity that would be needed to close the distance, to actually move fast enough relative to the expansion of space, to reach a point that is currently 220 million light-years away. The remaining 80% of the required velocity does not exist. And the reason it does not exist is that the structure producing the gravitational pull is not gravitationally bound, which means the expansion of the universe is already winning the contest between attraction and recession, already pulling the components of Laniakea apart faster than gravity can pull them together. Dark energy is responsible for this outcome. And dark energy is the name scientists give to a phenomenon they can measure with extraordinary precision but cannot explain in any satisfying mechanistic way. Its discovery in 1998, from observations of distant supernovae that appeared fainter than any expanding universe without acceleration could account for, produced a result that remains arguably the most unsettling finding in the history of physics. The expansion of the universe is not slowing down under the influence of gravity, as it would in any model built around matter and energy alone. It is accelerating. Something is pushing space apart at an increasing rate, and that something, which constitutes approximately 68% of the total energy content of the universe, is uniformly distributed through all of space, grows stronger as space expands, and has been steadily overpowering gravity on scales larger than individual galaxy clusters since roughly 5 billion years ago. Dark energy does not pull anything, and it does not push any particular object in any particular direction. It stretches the space between objects, so that the distance separating two galaxies increases, not because either galaxy is moving through space, but because space itself is expanding between them. The effect is negligible inside galaxies, negligible inside galaxy clusters, negligible even across the 100 million light-year scales of the larger clusters. But at the scale of superclusters, at 500 million light-years across, it is decisive. Laniakea, as a result, is not a stable structure. It does not represent a gravitationally bound system that will persist indefinitely into the future, the way the local group is bound, the way the Milky Way and Andromeda are bound to each other and will eventually merge in a collision roughly 4 billion years from now. Laniakea is a transient pattern, a momentary configuration of matter in a universe that is currently expanding fast enough to prevent the supercluster from collapsing on itself, but slowly enough that the flow lines toward the Great Attractor are still detectable and measurable. What Tully's team mapped in 2014 was not a permanent feature of the cosmic landscape. It was a snapshot of a structure in the process of dissolving. A basin that is currently directing the motion of its constituent galaxies toward a center they will never reach, because the basin itself is expanding away from that center faster than the galaxies can fall toward it. The Milky Way has been falling toward the Great Attractor for billions of years. The distance to the Great Attractor has been increasing for billions of years. Both of these statements are simultaneously true, and their coexistence is not a paradox, but a precise description of what happens when a gravitational pull that is strong enough to generate peculiar velocities of 600 kilometers per second is still only 20% as strong as it would need to be to overcome the expansion of the space it is trying to cross. We are falling, and the floor is rising faster than we are falling. Every billion years, we get a little closer in peculiar velocity terms, and simultaneously, the distance expands because the structure we are part of is not bound tightly enough to resist the stretching of space. The Great Attractor will recede. Laniakea will disperse. The 100,000 galaxies whose coordinated motion defines the supercluster will, over tens of billions of years, drift apart into the expanding void, each one eventually isolated within its own local gravitational cluster, separated from all other clusters by distances so vast that light will not be able to bridge them within any finite time frame. This is also, notably, what is happening to Shapley, the concentration that may be the basin within which Laniakea itself sits, 10 times larger by volume, containing thousands of galaxy clusters and a gravitational influence that extends across a domain whose far edge we cannot yet map, is also not gravitationally bound at the supercluster scale. The flows toward it are real, the motion they produce is measurable, but the same mathematics that prevents the Milky Way from ever reaching the Great Attractor applies at every larger scale. There is a size beyond which no concentration of matter, however massive, can prevent the expansion of space from eventually overwhelming its gravitational cohesion. and dispersing its components into the void. Shapley's gravitational influence, felt across 650 million light-years, will weaken as that distance grows. The flow will persist for some time, measured in billions of years, but the destination will always recede slightly faster than the traveler approaches. So the motion is real, the destination exists, and the journey will never end. This is the precise situation of the Milky Way and everything it contains, including everyone who has ever lived on any planet orbiting any star within it. There is an additional layer to this situation that becomes visible when you consider what the motion actually represents at human scales. 600 kilometers per second toward the Great Attractor sounds like a velocity that should eventually close the gap. And at human intuitive scales, it would. A car traveling at 60 kilometers per hour covers 60 kilometers in an hour. And any destination can, in principle, be reached by traveling long enough. The reason the same logic fails at cosmological scales is that the denominator in the calculation is not fixed. The Great Attractor is not sitting at a static distance of 220 million light-years. It is sitting at a distance that is actively growing. Not because the Great Attractor is itself moving away from us, but because the space between us and it is being continuously generated by the expansion of the universe. Inserted into the gap, the way new road is being laid between us and our destination faster than we can drive. Dark energy does not slow the Milky Way's peculiar velocity. It expands the space the velocity has to cross, adding distance at a rate that our 600 kilometers per second can partially but never fully compensate. The fate of Laniakea in this context is not dramatic dissolution on any human timescale, or even any timescale associated with the lifespan of stars. The processes at work here operate on tens of billions of years. And for a period measured in billions of years from now, the flow lines toward the Great Attractor will continue to be detectable in principle. The basin of Laniakea will continue to exist as a coherent gravitational pattern, and the Milky Way will continue its fall toward a center that remains perpetually out of reach. The dispersal of the supercluster is not an event with a date, it is a gradient, a slow diminishment of coherence. The gradual fading of flow lines as the expansion of space lengthens the distances over which gravitational forces must operate and reduces their effectiveness in proportion. The basin empties not by some catastrophic dispersal, but by the same quiet, patient process by which it filled. Galaxy by galaxy, cluster by cluster, each one drifting past the threshold where its peculiar velocity toward the center is outweighed by the expansion velocity of the space it occupies. What the Milky Way will experience, billions of years from now, is not arrival and not dispersal, but gradual isolation, the slow disappearance of the surrounding structure as the supercluster dissolves, leaving the local group and its immediate neighborhood gravitationally bound but cosmologically alone, disconnected from the larger pattern that currently gives our motion its direction and our address its meaning. The Great Attractor will not vanish. The normal cluster will remain as a gravitationally bound structure indefinitely, but the basin it anchors, the supercluster scale pattern of flows that makes it the center of our home, will have dissolved, and the Milky Way, still falling at 600 kilometers per second toward that center, will find itself in a universe where the structure it was part of no longer exists in any form that could be detected from within. But there is something even larger operating here than the contest between gravity and dark energy. A structure so vast that it makes both the Great Attractor and the Shapley Concentration look like features within a pattern, knots within a web. Details in a design that operates at the very largest scale the observable universe contains. In the very earliest moments after the Big Bang, the universe was smooth, not perfectly smooth. Quantum mechanical fluctuations ensured that even at the Planck scale, there were tiny variations in density, regions slightly denser than their surroundings, and regions slightly less dense, but the variations were tiny. The universe was hot and dense enough that radiation pressure resisted gravitational collapse. And for the first 380,000 years, the cosmos maintained a state of near homogeneity that left its thermal fingerprint in the cosmic microwave background. As the nearly but not quite uniform temperature map that was first detected in the cosmic me 1970s, when the universe cooled enough for atoms to form, radiation pressure dropped and gravity began its patient, inexorable work. The regions that were slightly denser than average had slightly more gravitational pull, attracting matter from their surroundings and growing denser still. Their increased density generating more gravitational pull, attracting more matter, a runaway process of hierarchical accumulation that, over the next 13 billion years, converted those primordial quantum fluctuations into the structure of the observable universe as it exists today. The process is called gravitational instability, and its output is the cosmic web, a three-dimensional network of filaments, sheets, nodes, and voids that constitutes the large-scale architecture of the universe at every scale above individual galaxies. The web is not metaphorical. It is a real structural feature of matter distribution that appears in every large galaxy survey ever conducted, confirmed by the Sloan Digital Sky Survey's maps of millions of galaxy positions and velocities, reproduced with extraordinary fidelity by computational simulations of structure formation that begin with a smooth, early universe and evolve it forward under the known laws of physics. Galaxies are not scattered randomly through space. They are concentrated along filaments, thread-like structures that can extend for hundreds of millions of light-years. And at the nodes where multiple filaments intersect, the density of galaxies is highest, producing the massive clusters that anchor the web's structure. Between the filaments and nodes are voids, regions nearly empty of galaxies that can span 30 to 300 million light-years in diameter, regions where the average density of matter is far below the cosmic mean and where, as a consequence, dark energy's influence is dominant and the expansion of space proceeds faster than in the denser surrounding regions. The structure of the web reflects directly the structure of the gravitational instability process that produced it. In the earliest universe, the slightly overdense regions that would eventually become filaments were not randomly located. They formed along planes and threads defined by the geometry of the initial density fluctuations. And as they grew, their growth reinforced their linear character, drawing in matter from adjacent underdense regions and depositing it along the elongated structures we now observe. The voids formed simultaneously, as the matter they once contained flowed outward along the gravitational gradient toward the surrounding overdensities, leaving behind volumes that became progressively emptier as the overdense regions grew denser and the evacuation of the voids accelerated. The result is a structure that has a mathematical resemblance to a spider's web, and also, more practically, to the distribution of bubbles in foam, with the galaxies located on the surfaces of the bubbles and the voids occupying their interiors. The Milky Way sits in a filament connecting the Virgo cluster to the Fornax cluster, a thread of the web that feeds into the larger node structure of the Laniakea supercluster. From any sufficiently elevated vantage point, the filament we inhabit looks like a single strand in a net that extends across the full observable universe. A net that, at the very largest scales, contains something on the order of 2 trillion galaxies distributed through a volume roughly 93 billion light-years in diameter, all organized into the same hierarchical web structure that produced the Great Attractor, the Shapley Concentration, and every other large-scale feature of the cosmos that the past century of astronomy has identified. The numbers associated with the cosmic web require some deliberate processing. Filaments can reach lengths of several hundred million light-years, meaning that a single structural feature of the web might extend for roughly 5,000 times the diameter of the Milky Way. End to end, the largest identified filament, the Hercules Corona Borealis Great Wall, spans approximately 10 billion light-years, a structure that contains within its length more than 70% of the observable universe's diameter. The voids between filaments can contain essentially no galaxies at all across their full extent. Vast three-dimensional spaces, where, if you were somehow transported to their interior, the nearest galaxy might be tens of millions of light-years in every direction. Distances that would make the isolation of our own Milky Way, surrounded by its local group of 50 galaxies within a few million light-years, feel positively crowded by comparison. The web also provides the framework within which the Great Attractor's position becomes fully legible. The Norma cluster, which sits at the gravitational center of the Great Attractor region, is a node, a point where multiple filaments of the web intersect and deposit their accumulated mass into a single, gravitationally bound structure. The flows that Tully's team mapped when they traced the boundaries of Laniakea are the flow lines of the web at the scale of a single basin, matter streaming along filaments toward the node at the basin's center. The same process that has been operating at every scale since the first overdensities grew dense enough to begin accumulating. The Great Attractor is not an anomaly within the web. It is the web's local expression, the nearest high-density node in our section of the cosmic structure, distinguishable from other nodes only by its proximity and by the fact that its gravitational influence extends across a volume large enough to encompass every galaxy whose motion we can currently measure with enough precision to isolate the peculiar velocity from the background expansion. Laniakea sits within this web as one node among many, a region of high density at an intersection of filaments, drawing in matter from its surrounding volume and contributing to the hierarchical accumulation of mass that the web has been conducting since the atoms formed. The Great Attractor is the highest density peak of that node, the gravitational center toward which the local filament structure converges. The Shapley Concentration is a larger and denser node in the same general region of the web, more massive and more dominant at the scale where its influence operates. All of it, every galaxy, every cluster, every supercluster, every attractor and concentration and basin of attraction, is simply matter distributed along the gravitational scaffolding that those primordial quantum fluctuations built over 13.5 billion years. And the cosmic web, like Laniakea, is not permanent. Dark energy is already doing to the web on the largest scales what it is doing to Laniakea at the supercluster scale, stretching the voids, pushing the filaments apart, gradually eroding the connectivity of the structure. Research published in March of 2026 found that cosmic voids are not passive empty spaces between the web's structural elements. They are active participants in the universe's evolution, expanding under the influence of dark energy and pressing against the surrounding filaments with a mechanical force that, over cosmological time, is slowly pulling the web apart. The voids are where dark energy's work is most clearly visible, because within the voids there is so little matter that the gravitational counterforce that dark energy must overcome is minimal. In the densest regions of the web, inside galaxy clusters, inside galaxies, inside solar systems, dark energy's influence is negligible, overwhelmed by local gravitational forces. But in the voids, which account for the majority of the universe's total volume, dark energy dominates, and it is converting that volume into an ever larger reservoir of accelerating expansion. Over the next 5 to 10 billion years, estimates that vary depending on assumptions about dark energy's future behavior, the cosmic web's large-scale structure will gradually dissolve. Filaments will thin as the galaxies strung along them drift apart into expanding voids. Superclusters will disperse as their gravitational basins fail to hold their contents against the stretching of space. What will remain are the gravitationally bound structures that are small enough and dense enough to resist dark energy indefinitely individual galaxies and their satellites. Galaxy groups, like the local group, and the galaxy clusters that represent the largest structures capable of maintaining coherence against the expansion. Everything above the cluster scale will, over tens of billions of years, gradually fade into isolation. The universe's future is a collection of island universes separated by voids so vast that no signal traveling at the speed of light will ever cross them within a finite time frame. From inside one of those islands, say, a future version of the Milky Way Andromeda merger product that will form when our galaxies collide in approximately 4 billion years. The rest of the universe will be invisible. Other galaxy clusters will have receded past the cosmic horizon, their light red shifted into invisibility by the accumulated expansion of the space it was crossing. The cosmic microwave background will have cooled to near absolute zero. The web, the superclusters, the Great Attractor, the Shapley Concentration, all of it will have dissolved or receded beyond detection, leaving a single gravitationally bound island in an otherwise dark and empty cosmos, with no visible evidence that any of the structure astronomers are mapping today ever existed. This is not speculation. It is the direct physical prediction of the standard cosmological model, confirmed by 5 decades of increasingly precise observation. And it is the context within which the motion of the Milky Way toward the Great Attractor takes on its full meaning. The question that opened all of this was not merely astronomical. It was personal in the way that the deepest questions about place and belonging always are. In a universe where everything is moving, where the galaxy we inhabit is being pulled at 2 million kilometers per hour toward a gravitational center we will never reach, where that center is itself being drawn toward a larger structure that is itself dissolving under the influence of a force comprising 68% of the energy of the universe. In that universe, where is home? And where are we going? Consider what it took to arrive at the shape of that question. In the 1970s, the data that would eventually point toward the Great Attractor was a temperature asymmetry in the cosmic microwave background so small that it required years of careful measurement and instrument calibration to distinguish from noise. The peculiar velocity it implied was a residual, what was left after subtracting out everything the universe was supposed to be doing anyway. Stripping away the Hubble expansion, the orbital motion of the Earth around the Sun, the orbital motion of the solar system around the Milky Way's center, the motion of the Milky Way relative to the local group's center of mass. And what remained after all those subtractions was 600 kilometers per second, aimed at a constellation whose most prominent feature was a modest cluster of stars that the ancient Romans named after a carpenter's square, detecting the gravitational influence of 100,000 galaxies distributed across 500 million light-years from a thermometer reading of less than 1/100th of a degree Fahrenheit is, by any measure, one of the more extraordinary achievements of the human intellect in any domain. The journey from that temperature measurement to the map of Laniakea took approximately 40 years. It required the development of new observational techniques, the construction of new telescopes operating across multiple wavelengths, the accumulation of redshift and distance measurements for hundreds of thousands of individual galaxies, the development of computational tools sophisticated enough to process that data into 3-dimensional velocity fields, and the conceptual insight to recognize that peculiar velocities could serve as a proxy for gravitational landscape. In the same way that flow directions on a landscape serve as a proxy for topography, the 7 samurai contributed to this effort, as did dozens of subsequent teams working with successively larger datasets and more refined methods. The Cosmic Flows Project, The systematic effort to catalogue peculiar velocities across the local universe that produced the Laniakea discovery and its subsequent refinements has been running since the early 2000s and is still generating new results. Most recently, the 2024 study that placed a 60% probability on Laniakea itself being a sub-basin within a Shapley-centered structure, 10 times its volume. The answer that 50 years of cosmological investigation has assembled is stranger, and in some ways more satisfying, than any of the simpler answers that were available before the work began. Home turns out to be not a location but a structure, specifically a gravitational basin defined by the flows of 100,000 galaxies converging toward a shared center over a volume of space 500 million light-years across. We did not know we lived in this basin until 2014. We had been inside it for the entire history of the solar system, for the entire history of life on Earth, for every moment of human existence, moving toward its center 600 kilometers per second without any awareness that the motion was happening. The discovery of Laniakea did not create our home. It revealed that we had been inside it all along, the way a fish discovers water, not by entering it, but by developing the instruments to detect it. And the basin keeps expanding in the telling. Laniakea. It turns out, with its 500 million light-years, and its 100,000 galaxies, and its 100 million billion solar masses, may itself be only a sub-region of a larger basin anchored by the Shapley Concentration, a structure 10 times larger in volume, whose full extent may lie beyond the reach of current surveys to map. The pattern of nested discoveries, each answer revealing that the previous answer described only a room within a larger room, has repeated itself at least 3 times since Hubble first catalogued galaxies in the 1920s. And there is no obvious physical reason to expect it to stop at Shapley. The universe may contain basins of attraction beyond Shapley, structures operating at scales that no instrument currently planned could resolve, exerting influences on the motion of our galaxy that are real but too diffuse and too large to isolate from the background. The map of home has edges that are perpetually receding. What this means for the question of destination is equally striking. The Great Attractor is where the flow of Laniakea converges. It is the gravitational center of the structure we call home, the low point of the basin, the focal point of the flows, the place toward which 100,000 galaxies have been drifting for billions of years. And it is a place we are moving toward in every astronomical sense of the word, at a velocity that is real, measurable, and persistent, a velocity that will continue for billions of years into the future, carrying the Milky Way steadily in the direction of Norma and Centaurus at 600 kilometers per second for as long as the structure of Laniakea remains detectable as a coherent pattern. The journey toward home is genuinely happening. It will never be completed. The basin is dissolving as we fall through it. Dark energy stretching the walls and floor of the structure we are trying to descend into, expanding the distances that gravity is trying to close. The destination exists and it recedes. The motion is real and it will never terminate in arrival. This is the precise physical situation of a galaxy that has peculiar velocity toward a supercluster that is not gravitationally bound, which is to say, it is the physical situation of the Milky Way and of everything it contains. There is something worth pausing on in the structure of that situation. Something that is not merely an astronomical curiosity, but a feature of existence at every scale the universe contains. The forces that shape the large-scale structure of the cosmos, gravity pulling matter together, dark energy pushing space apart, are in permanent tension, and neither ever completely wins at the scales where both are operating. Below a certain mass threshold, gravity wins, galaxies are bound, galaxy groups are bound, galaxy clusters are bound. Above that threshold, dark energy wins, superclusters dissolve, basins of attraction disperse. The web unravels. The scale of our home, Laniakea, sits precisely in the contested zone between those two outcomes. Too large to be gravitationally bound, too coherent to be already dissolved. A structure that is simultaneously real and temporary, defining and dissolving. Home and in the process of dispersal. The Milky Way, from its position near the edge of Laniakea, is part of a flow that is real and directed and cosmically meaningful. Moving toward a gravitational center that organizes the motion of 100,000 galaxies, it is also moving towards something it will never reach. Falling into a basin that is simultaneously pulling it inward and expanding away from it. Carried along in a current that was shaped by the distribution of matter in the early universe and is being gradually erased by the energy content of the space through which it flows. The cosmic address of our galaxy at this moment in the universe's history reads outskirts of Laniakea, in motion toward the Great Attractor, within a gravitational basin that may extend to Shapley, embedded in a node of the cosmic web, in a universe whose expansion is accelerating. That address has been assembled piece by piece over 50 years of observation, each piece added by someone pointing a telescope at a region of sky that most people had never heard of, and asking a question that most people would not have thought to ask. The peculiar velocity measurements of the 1970s were not motivated by a search for home. They were motivated by the desire to understand whether the expansion of the universe was truly uniform. And the discovery of the asymmetry was a byproduct of that more abstract inquiry. The seven samurai were not trying to identify our supercluster. They were trying to map the distribution of mass in the local universe. And the Great Attractor emerged from that effort as an unexpected structural feature whose implications took decades to fully trace. Tully's Laniakea paper was not presented as a discovery about belonging or address. It was a technical paper about a new method for defining the boundaries of superclusters using peculiar velocity data, and its broader meaning accumulated gradually in the months and years after publication, as astronomers and science communicators worked through the implications of what it meant to have, for the first time, a physically defined boundary around the structure we call home. The knowledge of where we are and where we are going was assembled not by anyone seeking that knowledge in particular, but by the accumulated pressure of scientific curiosity applied systematically to the universe's most fundamental questions about structure, motion, and the distribution of matter across cosmic scales. That is not a permanent address. It is a description of a moment in a process, the moment when the structure is still coherent enough to read, before the expansion has dissolved the filaments and dispersed the basins and left the Milky Way as one island in a dark and empty cosmos, with no external structure left to belong to. The home that cosmology has revealed is real, vast, and temporary. The destination is real, distant, and unreachable. The motion is real, sustained, and will outlast everything that currently makes the universe feel structured and organized and legible. Every civilization that will ever exist on any planet in any galaxy within Laniakea is riding the same flow, directed toward the same center, part of the same transient gravitational choreography, whose coherence will persist for billions of years and whose dissolution will take billions more. The question of where home is has an answer. Then, and the answer is that home is the motion itself. It is the fact that 100,000 galaxies, distributed across 500 million light-years of space, are all participating in the same gravitational choreography, all flowing toward the same center, all defined by their membership in the same basin of attraction that astronomers named Laniakea in 2014 after a Hawaiian word for immense heaven. We are part of that flow. We have always been part of that flow. We will continue to be part of it for billions of years, moving toward a center that retreats as we advance. belonging to a home that is in the process of ending, falling through a structure that is real and enormous and dissolving. And in the cosmic web, at the scale where all the basins and attractors and superclusters are simply features of a larger pattern. The flow toward any particular center is just the local expression of a universal process. Matter following gravity, gravity shaping structure, structure shaping motion. All of it unfolding from those primordial quantum fluctuations in the first fraction of a second after the universe began, playing out across 13.5 billion years of cosmic time, arriving at this particular configuration, at this particular moment, in which a small, rocky planet in the outer spiral of a medium-sized galaxy near the edge of a dissolving supercluster is able to look outward into the sky, measure the motion of 10,000 galaxies, and ask where it is going. The universe does not answer that question in words. It answers it in velocities, in flow lines, in the coordinated drift of 100,000 galaxies toward a gravitational center that organizes the largest structure we know ourselves to be part of. The answer is 600 kilometers per second in the direction of Norma and Centaurus, toward a place we call the Great Attractor, within a home we call Laniakea, falling through a cosmos whose expansion will eventually leave us alone in a way that makes the current loneliness of space seem, by comparison, almost intimate. There is something in the sequence of discoveries, the temperature asymmetry, the peculiar velocity, the seven samurai, the zone of avoidance, the Norma cluster, the Laniakea mapping, the Shapley re-evaluation that follows the pattern of a long unwinding. Each discovery added detail not by replacing what came before but by extending it, revealing that every previous answer had correctly described a layer of reality while missing the layer above it. The Milky Way's peculiar velocity was correctly measured in the 70s. The Great Attractor was correctly identified in 87. The Laniakea Basin was correctly mapped in 2014. The Shapley Subbasin was correctly suggested in 2024. None of these findings contradicted any of the others. Each one enlarged the picture, and the picture is still enlarging. The instruments currently being planned and built, the next generation of large-scale galaxy surveys designed to map peculiar velocities across billions of light-years rather than hundreds of millions, will almost certainly reveal another layer, another basin within which the Shapley concentration sits as a local feature of a still larger structure. The map of home will grow again. The address will lengthen. The question of where we are going will extend outward to encompass another scale at which the same dynamics, gravity pulling, dark energy pushing, flows converging towards centers that are simultaneously real and dissolving, are playing out at proportions that make Laniakea look small. That is where we are going. That is what home is. And the fact that we can know it, that 50 years of astronomical patience and ingenuity and instrument building have produced a map detailed enough to place us within this structure, to identify the direction of our motion, to name the basin of attraction we have been flowing through for the entire history of our planet, is the most remarkable fact in a story full of remarkable facts. The universe is enormous, and moving, and dissolving. We are inside it, flowing with it, named within it. For now, in this brief cosmological moment, before the web fades and the basins disperse and the islands drift into permanent isolation, we know exactly where we are